All right. Hopefully we can hear me, see me. We are ready to go. Today's lesson I'm going to try to keep short because it's only two examples, this one and this one. This one is a good intro warm-up, and the next one is kind of an AP style question of the same content. And this is honestly practicing pretty much everything we learned from the previous day. So on the concavity and on the increasing and decreasing, all those tests that we learned in the previous lesson. This is putting all that into practice with sketching a curve. Now, we did this as one example in the previous lesson. But now we're going to talk about how to take an equation and find all these points, all these intervals, and use these intervals to sketch the original graph. So the original graph in this case, there we go. The original graph in this case is 2x to the fourth minus 3x squared plus 2. And I might have a graphing calculator, and I may be able to graph this, but we're going to graph this without using anything but calculus and math. Okay, we're going to use all these abilities to graph it. Okay? So we're going to find all these intervals. We're going to start off with our critical points, increasing, decreasing, relative max and relative min, and then inflection and concavity. Okay, so this first section here that I got, these from critical points down to relative min, that's all found from our first derivative, and inflection point through concavity, that's all found with our second derivative. So I'm going to come back up to this, but I'm going to show you the process that we do every single time, and we're going to do it. I'll do it below here. Okay, so remember, my f of x equation is 2x to the fourth minus 3x squared plus 2. Okay. Now, all the first information comes from that first derivative. So we're going to start by finding our first derivative, and that's nothing too crazy. That's just a couple power rules here. 8x cubed minus 6x. Okay. Now, we're going to go down the list, and this is gonna help us find everything we need to. We need to set it equal to 0 and solve for a few points. Same thing with our second derivative. But let's start with our first one. Okay, I'm going to set it equal to 0. And this isn't anything too crazy. I think I can take out a 2x, left with 4x squared minus 3. So x equals 0. Let's see, x squared equals 3/4. So x equals plus or minus the square root of 3/4. And if you want to simplify that even a little bit further, you could say plus or minus the square root of 3/2. Okay? All right, so we got our critical points. 0 plus or minus the square root of 3/2. That's where my derivative is equal to 0. Now, as to the left and right of these points, where they're either all positive or all negative. Okay, so those tell me the interval in which it's increasing and the interval in which it's decreasing. Okay, so I'm going to keep track of that right maybe here. Okay, so on this number line, it looks like my critical points are negative √3/2. We got 0, and we got positive √3/2. Okay. So what can I tell from all that? Well, if I test points in between these values, okay, we can figure out the interval if it's negative or positive. So I'm kind of curious what √3 divided by 2 is. That's 0.866. It's 0.866, so approximately 0.866. That'll maybe help us gauge which values we can plug in. All right, so how about, like, if I'm testing it, I'll test these values in the first derivative here. So maybe I'll test a point to the left of negative 0.866, maybe like -1 or -2 or something like that. And if I plug something into that, okay, so this is going to be a negative number times in the parentheses, that would be a positive number if I plug in something big enough. So the negative times a positive is a negative. Now, what about like a number to test between negative 0.866 and 0? Maybe like -1/2. That's going to be a negative number times, and this will end up being a number less than 3 minus 3. It'll be a negative number as well. So negative times a negative is a positive. Testing other points, we actually get negative and positive as well. Okay, so you have those points you can test. And with that information, we have all we need to answer the first parts of this question. Okay, so this is everything we can find from the first derivative. So let's go up here and label everything. Okay. First of all, the critical points are what makes it undefined and 0, and there's nothing that makes it undefined, but there is things that make it equal 0. That's x equals 0 plus or minus root 3 over 2. So those are my critical points. Okay. 0 and plus or minus square root of 3 over 2. All right, now it's increasing on the interval where the derivative is positive, because that means we have a positive slope. So it's increasing from negative root 3 over 2 to 0, and from root 3 over 2 to infinity. That's just where you have the positive values. Okay. And it's decreasing where we have a negative slope, obviously, right? So negative infinity to negative root 3 over 2, and from 0 to root 3 over 2. Okay. And the other thing that we can find from the first derivative is relative max and min on this interval. And that happens at potential critical points. So we get that from this number line here as well. It's where it's changing from negative to positive, then it's a minimum. Think about it. We're decreasing here, and then we're increasing here. So that must mean that makes a little like valley looking shape. That is a minimum. So we have a relative minimum, okay, at the point negative root 3 over 2. And we'll figure out that y value in just a second. Okay. At 0, it's going from positive to negative, so that's the opposite. That's going to be a maximum. It's going from increasing to decreasing, so that's a maximum value. So we have a point at 0, and again, we'll find that y value in a second. And lastly, it's going negative to positive, so again, that value right there is going to be a minimum. Oops, and that's positive. Okay. Now, if you want to know the y values of your relative max and your min, and that's very helpful because you want to be able to plot these points when you're sketching the graph. You want to plug these values back into your original equation. So if I plug 0 into that, for instance, I get 2. Now I'll let you try this on your own, but if you end up plugging in, you can do this in your calculator or just in your on your paper. It shouldn't take too long. But if you plug in negative root 3 or positive root 3, you get 7/8. I'll let you do that on your own, but we get 7/8. Okay? So that's everything that we can get from the first derivative. Everything that we can get from the first derivative. Now, let me do the second derivative. Let's talk about all the stuff we can get from the second derivative. Again, we learned all this in the previous lesson. All right, so first of all, the second derivative is equal to the derivative of 8x cubed minus 6x, which is going to be 24x squared minus 6. And we're going to set this equal to 0. All right, we're going to set this equal to 0 and see what we're dealing with here. So if I solve that, it's not too bad. We get x squared equals 6 divided by 24, or 1/4. And I can take the square root of that. And I get plus or minus, well, the square root of 1/4 is 1/2. So plus or minus 1/2. Now, this right here is an inflection point. Okay, those are my inflection points. So inflection points occur at positive 1/2 and negative 1/2. And we'll get those y values here in a second. Well, okay, I guess we can go ahead and do that now. If I want to know the y values of my inflection points, just go ahead and plug those again into your f of x equation. I'll give you a second to do that now, but I'll go ahead and give you what those values are. I'm getting 11/8 for both of them. Okay. All right. So we got our inflection points. We're going to put those inflection points. I like to, this was the derivative, by the way. I like to do the second derivative usually on the same number line if I can, just kind of like acceleration and velocity. Okay. I'm going to put negative 1/2, which is about right here. And I'll put positive 1/2, which is about right here. Now, testing points in this derivative to the left and right of these, and I'm going to test them into my second derivative equation. If I plug anything to the left of negative 1/2, maybe like -1, -2, whatever, it's going to be positive. Let's say I plug 0 into that, I get negative. If I plug in a positive number greater than 1/2, like 1, 2, 3, 4, it's going to be positive again. So the positive and negative from our previous lesson, we know those tell us concavity. It's concave up from negative infinity to negative 1/2. And also from 1/2 to infinity. It's concave down between negative 1/2 and 1/2. Okie dokie. So it is these values, these increments, all these points and all these intervals is going to help me to graph this function. It's going to help me to graph this function. So what I'm going to do is this. I believe I have room right here. Okay, this is how I suggest doing it. I always start by graphing the points that I have first, not the intervals, but the points. So for instance, I got the critical points. They are my relative maxes and my relative mins. I start by graphing those points. So we got over 0, up 1, 2. I don't know why I put 0, 0. Okay, so we got over 0, up 2. There's my first point. Okay. And I know that's going to be a relative max, so keep that in mind. And then I got negative square root of 3 over 2, 7/8, and positive of the same thing. So how that works is, okay, that's negative like 0.8 something, and then it's a little less than 1 on both sides. So I'm going to go, the point's about like right here and here for my relative mins. And you can verify that, but again, it looks like that I'm going a little less than 1 in both directions, up and down. So something like that. Okay. So I got my relative maxes and I got my relative mins. I'm going to keep that in blue. Now what I'm going to do in green here is I'm going to do the other points that I got, which are my inflection points. Those are usually in between your relative maxes and mins, where you change concavity. So in this case, that's 1/2. Okay, let me make sure I get this right. 1/2 11/8. So 1/2 is like right here. 11/8 is a little bit more than 1. It's like right here. Same thing on both sides because it's 1/2 and negative 1/2. Okay. All right. Now we bring in the intervals. The intervals tell us the direction it's going and the curvature. Okay. Okay, so if I'm graphing this, you start with the increasing and decreasing. And I always recommend using this number line here if you can. Use this number line here. This is what I always use. Originally it goes negative, positive, negative, positive. That means we go decreasing, increasing, decreasing, increasing. That's what that tells us. Don't write that down. Please don't draw that. But if I were to look just at the first derivative, that's the only information it tells us, is that we're decreasing, then increasing, then decreasing, and then increasing. Negative, positive, negative, positive. But that is not the correct graph. Okay, that's not what it looks like. We know that these graphs are curves. They have curvature to it. So we know that it's going to follow that path, but we got to also, there we go. We got to also follow the same curvature. And that's where the second derivative comes into play. Okay? All right, look. From negative infinity up to negative 1/2, which is this green point here, it is concave up. So what that looks like is this shape here. Okay? It's still following the same intervals before. We're still decreasing. We got the relative minimum, and then we're curving up to this point of inflection. Okay? That is concave up. But between negative 1/2 and positive 1/2, we change concavity. We go to concave down because it's negative. So this is still going to become this is still going to be a maximum right here, but the concavity changes a little bit. You see how it goes from concave concave up to concave down. And then past 1/2 on my number line here, so from 1/2 on, it changes concavity to concave up. So there you go. So you see, with the second derivative, it's not just those straight lines, down, up, down, up. We add the curvature to it with the concavity. And that's what this graph looks like. So if you were to graph this in your y = equation or in Delta Math, this is the shape, generally speaking, that you would get. Okay? And that's how curve sketching works. That's the steps every single time. Finding these points. And that is exactly what you're going to be practicing on a little worksheet that I got you. We'll be practicing this tomorrow as well. Okay? So, good problem. Now, we're 16 minutes into the video. I would like to complete this example as much as I can. I promise I won't go over 30 minutes here. This is a good example because it's a free response question. I mean, this is from, it's an old one. This is 1980 BC question number 7. So things were done a little bit different back in 1980, but the questions are still pretty much accurate. Okay, so we got a lot of good review. Let's just see how much we can get through. So hopefully you have this available because I'm going to be scrolling down and up a lot. So have this question available on your other, print it out or something like that, or copy down. Okay. This is a great question to ask. This is a very common question that they do. They love to give you, notice what they're giving you. They're giving you the graph of the derivative. They're giving you the graph of the derivative. So let's see what we can do. This is the graph of the derivative, not of the function. Okay, keep that in mind. Let's read through this. It says, let f be a function that has domain the closed interval -1 to 4, which we can see here's -1 all the way to 4. So the function is between -1 and 4. And the range, the closed interval, -1 to 2. Okay, so -1 to 2. We're going to let f of -1 be -1, f of 0 be 0, and f of 4 equal 1. So we're going to keep all that in mind. And also let f have the derivative function f prime that is continuous and has the graph shown in the figure above. So all that's information overload now. We'll come back to those pieces of information as we need it. So let's go. Let's see if we can do this problem. Part A. A says, find all values of x for which f assumes a relative maximum. Justify your answer. We always, I teach it this way, I say we always start with the justification. It helps guide my process. It helps me figure out what I'm trying to find. So, by definition, when does f have a relative maximum? Okay? We're going to say f, I always literally repeat this. I'm just trying to get you in good habits of how to get these questions right. Say, f has a relative maximum when? Okay, so start with the justification. F has a relative maximum when what? What did we learn? Based off the first derivative test, it's when f prime of x changes from positive to negative. Okay. Has a relative max when f prime of x changes from positive to negative, right? Remember, if f prime is positive, it's doing this in the original function, and then is doing this when f prime changes to negative. So that makes a maximum. Well, let's look up above. This is the graph of the derivative, okay? Not the original function. This is not a maximum in the original function. That's a maximum on derivative, not the original function. Well, look at your justification again. F has a relative max when f prime changes from positive to negative. In this equation, when does f prime change from positive to negative? 2. Positive values, negative values. It goes from positive to negative values. X equals 2. And that's the only point on this graph where it goes from positive to negative. So that's why I think it's very important to start with a justification so you can find the answer really quick. B. B says find all values of x for which f assumes its absolute minimum. Justify your answer. Again, we are going to start with the justification. And this is where the justification comes into play. Absolute minimum or maximum, the justification on a closed interval, extreme value theorem. So we're going to say by the extreme value theorem, f is guaranteed. Is that how you spell guaranteed? I don't care if it is or not, whatever. By the extreme value theorem, f is guaranteed an absolute minimum value on the interval, on the closed interval, -1 to 4, because it is continuous and differentiable for all x on the interval. Okay? So by the extreme value theorem, f is guaranteed an absolute minimum value on -1 to 4 because it is continuous and differentiable for all of x on the interval. That's the extreme value theorem. So we know we're guaranteed an absolute minimum. This will occur, this is again based off of how extreme value theorem works. This will occur at an endpoint or critical point. So we're going to look at all of them. And to be perfectly clear, a critical point that goes from negative to positive. That's the definition of a minimum, is it goes from negative to positive. So we're going to look at endpoints, and we're going to look at critical points that go from negative to positive. Let's start with critical points that go from negative to positive. The critical points are right here at 0, 2, and 4. It's points that that make the derivative equal to 0, right? It's where the derivative equals 0, 2, 0, and 4. Now look at all of those points. Are any of those points going from negative? I'm sorry, that's positive. Are any of these points going from positive to negative? Are any of them going from positive to negative? Here it's going positive to positive. Here it's going positive to negative. And here it's just negative, but I don't know what's going on past 4. So there are no critical points to check here because none of them are going from negative to positive. This is positive to negative. This is negative to whatever. And this is positive to positive. So there are no critical points to check. So we're going to specify that. No critical points go from negative to positive. So we're just going to check the endpoints. Okay, the endpoints will be f of -1 and f of 4. Now, here's the cool thing. Please do not make this mistake and go over to -1 and say this is the value of -1 and this is the value of 4. This is the derivative function, not the original. So how do we figure out the values of -1 and 4? Well, it's told in the problem. And that's the whole point of them telling you in the problem to help you with part B. So f of -1 is -1. And f of 4, it looks like the original value is 1. So based off of that, this is going to be our relative minimum. So this question for B specifically says find all values of x for which f assumes its absolute minimum. So that's going to be x equals -1. A long justification, but this is the time that I was talking about, where the only time we'll use the extreme value theorem to explain on a closed interval that we are indeed going to have an absolute extremum. Okay? All right, I'm running kind of behind here. Let's see how much more I can get done before 30 minutes. Part C. Part C says find the intervals on which f is concave downward. All right, this is something that I'm really going to explain in class. I'm going to summarize this again in class. Any justification that you ever give, justify your answer, justify your answer. It doesn't ask you to justify the answer in C, but we're going to do it anyway. It's always got to be justify in terms of graph given. You always have to do it in terms of the graph given and the information given. Since we're given the derivative, we have to talk about the explanation in terms of the derivative. So when is something concave down? We know that's when the second derivative is less than 0. It means that we're concave down. We're not going to use that explanation. That's another, when derivative is concave down. Uh-oh. When a derivative is concave down, I better get my battery charger here in a sec. When a derivative is concave down, that means that the derivative function, all right, is negative. If a derivative function is like a negative slope, like it's going down, that means the second derivative is going to be negative. So what intervals is the slope of this graph going down? Negative. From -1 to 0 and from 1 to 3. That has a negative slope, which means the second derivative is going to be negative. All right? The slope of the derivative graph makes the concavity negative. It means my second derivative is negative. So -1 to 0, and from 1 to 3, my slope of my derivative graph is 0, so that means f double prime is less than 0. So let me write out how we're going to explain that. I'm going to get my battery charger real quick. Okay. F is concave down. And we know it's concave down when the second derivative is less than 0. But in terms of the derivative, we're going to say when f prime of x has a negative slope. A better way of saying that is decreasing. A negative slope, that's the same way of saying that f double prime is less than 0. Okay? And we already showed that on the graph. That happens between -1 to 0 and from 1 to 3. All right. Now, based off of time, 28 minutes. I promise I never go over 30. And plus my fourth period class is about to come in. We will do D and E together as a class. Try it on your own, though. All the values where we have a point of inflection. Think about how that's going to look in terms of my derivative graph. Point of inflection. We know that's where f double prime of x is equal to 0 or does not exist. It's like a critical point for a second derivative. So think about how that would look on this function here from the derivative graph. And then we'll talk about how to sketch it later. So we should be able to get most of this done in class. And so we'll have a predominant amount of class to review and refresh and do some practice. Okay? All right. Well, I hope you'll have a great day. Oh, let me do my smiley, star, and heart. I can't remember if it's that order or not, but there you go. Okay. Y'all have a great day.